Now let's talk about how to do model selection when you're doing causal inference. And in this case, what we're trying to do is minimize the bias of our estimate and also, of course, the variance. If we could be more confident without sacrificing bias, that would be great too. So this is in contrast to in the predictive case where all we want to do is get the best predictions. Here, we don't actually care about the individual level predictions. We just want to know how close is the overall effect estimate to the truth. Of course, we don't know the truth, right? So this is a little bit different. So you can already see, right, depending on what the question is, you're kind of asking different things of the model, and you're going to have different approaches. So the first thing to notice is that if we're going to focus here, by the way, on variable selection. So what variables should you include? We're not going to talk about so much what kinds of nonlinearities or splines or things like that should go in. We're just going to talk about what variables you should include, and we'll talk more about how you do the actual like complexity selection and stuff in maybe like 2 or 3 weeks, a little bit more. Just suffices to say that what we said in the first lecture about linear regression holds, which is that there is still a kind of model misspecification bias. If you're only including linear terms and the real relationship is nonlinear, then you're going to have bias. So you can think of, if you're not including a particular squared part of a confounder, that's kind of like leaving out an unmeasured confounder if you're not putting that in there. But we'll talk a little bit more about that in a couple weeks. So just hold that thought. For now, just consider, should we include a variable at all or not? So one easy case is if a variable is post-exposure, you should not include it, okay? And here is a simple case where you have what's called a collider between the exposure and the potential outcomes. And you want to know, okay, what would happen if in my regression model, where I'm estimating the effect of A on the observed outcome Y, what would happen in the regression model if I regressed Y onto A and C? If I did this in R, and then let's say I looked at the coefficient of A, or I did the plug-in estimator to get the marginal effect of A on Y, what would happen if I included C? Is that good to do or not? And it's not good to do. And the reason why is because, remember from our identification lecture, what we're trying to get is the expected value of this potential outcome to equal to something like this that doesn't have any potential outcomes in it, where we're just conditioning on A. And we saw that in order to get that, we can assume that if we have Y, the potential outcome is independent of the treatment given some covariates, then this holds. But the problem is that in this setting, C is a collider. So here we have a setting where actually A is already independent of YA. Why? Because there's only one path from A to YA, and it goes through C, and C is a collider, and so it blocks that path. So they're already independent as it is. However, if I condition on C, because C is a collider, conditioning on it unblocks that path. So by conditioning on C, I've messed up the independence, right? So we no longer have that independence, which means that this identification result no longer holds. And if you recall, the proof of this is just some total expectation, and then exploiting this conditional independence property to factor something. So it's not terribly difficult. You can go back and review that if you want, but it really just holds on this key conditional randomization assumption, and in this case, it's just not satisfied. So you should never condition on a collider, or more generally, anything that is after the exposure, because anything that happens after the exposure could be a collider. It's either a collider, it could be a collider if it's something that happens after the outcome, right? So definitely don't condition on anything after the outcome, because that's potentially a collider. But actually, turns out even anything that's after the exposure, so what's the other case? Maybe it's a mediator, right? Maybe it's something that's after the exposure, but before the outcome. So it could be something like this, right? Where we have A affects M, which is this mediator variable, which then affects Y. Okay, can we condition for that? Kind of naively, you would say, okay, in this graph, if I condition on that, it blocks this path. But maybe that's okay because this is on the path. It's not a collider, so what's the big deal? But this is not the right DAG to be looking at. This is the observed world DAG. But what you need is the conditional independence between A and Y little a, the potential outcomes. And in the potential outcome world, the DAG looks something like this, right? You have A, and then you have the value that the mediator would have taken if A were a particular value. So this is like the, when I write YA, I mean YA1 and YA0. So here you think of this as like YA1, Y where A equals 1, and then M where A equals 1. And then you have this other universe where the treatment is always 0. So it's, this is really what I'm trying to represent. And so these are two kind of parallel universes, like the bad twin universe and the good twin universe. And it doesn't really matter in our universe what A gets observed to be. That doesn't affect what happens in these parallel universes where everyone is always treated or nobody is ever treated. But this is what we actually need to think about. We need to care about the is Y, little a independent of A given some stuff. That's what we actually care about, not Y little a. So this is the picture we should be looking at. And the question is, okay, if we condition on the observed value of the mediator, what happens? Well, where's the observed value of the mediator? That here we have only the potential outcome, the potential values of the mediators. What's the observed value of the mediator? Well, the observed value of the mediator is whichever one of these corresponds to what A was. So again, if you're thinking about like in R in your data generating process, this is like M is equal to if else A M1 M0. Okay. So this clearly depends on the M0 and the M1 and A. So what happens? This is now a collider. Why? Because, look at the path. Between Y1 to get to A. The path goes like this, right? And M here is serving as a collider. So if I condition on it, it then removes that collider, and information can flow, and therefore these things are not conditionally independent given M. So that's why you cannot condition on a mediator, because a mediator is effectively a collider in the causal world. It's kind of subtle. And I haven't seen this really explained in a lot of other classes. They just say, well, don't condition on a mediator because it is kind of part of the effect that you're trying to measure. But I think it helps to concretely understand why, in terms of conditional independencies, that induces bias, right? So effectively, we have this. If I have my linear regression and I put M into the model, right? Because what I'm trying to do is condition on M. I'm trying to get the conditional expectation. This regression model is going after this conditional expectation, right? Y given A equals A and M. That's what I'm trying to estimate with this regression model. But this is not the same as this. Why? Because this conditional independence does not hold. So mediators are actually colliders. Colliders are things you should not condition on if you're trying to estimate causal effects. You may ask, okay, well, isn't there some kind of test that I can do to see whether something is a collider or not? Because maybe, okay, yeah, something happened after the treatment and after the exposure, but does that necessarily mean it's a collider? Maybe it was only affected by treatment or only affected by exposure or something like that, and then it wouldn't be on a path between the two. But there's no way to tell. There's literally no way to tell from data alone what is a collider and what is a confounder. Because if you remember, I can reverse the arrows in this DAG. This is the observed data DAG, right? I can reverse the arrows in this DAG and it represents the exact same distribution. So I can just factor one way, I can factor the other way. So there's no way to tell there's no way to distinguish which of these is more likely in a kind of a causal sense. They both actually represent the same distribution. And so there's no statistical test that can really distinguish them. So you have to rely on your domain knowledge to exclude colliders and mediators. So you have to understand more broadly the context in which these data are generated, the kind of processes, when things happened, in order to think about whether something is a collider or mediator. And the easiest way by far is to just never adjust for anything that happens after the treatment. Don't do it. Don't do it, okay? So anything that, if you have a timeline and you're thinking about when these data are being generated for a particular person, anything that happens before exposure, fair game. Anything that's measured after exposure, don't adjust for it. Now, that's actually a lot easier said than done, because in retrospective data, there's often no clear time of exposure. And often when you're comparing exposure to no exposure, okay, you can see when somebody got exposed, but when is it that somebody was not exposed? So I'll give you an example of that. So no clear time of exposure. Let's say that you're working on a study, and you want to know, are people who are living, if I could causally affect where oil wells were put. So that maybe we're afraid that people who live near oil wells are having lower birth weight babies. This is deleterious to health in many ways. So I want to causally understand if I could move people further away from oil wells, or more concretely, if I could ban oil wells from being put in places where a lot of people are living, how would that affect birth weights of children or other health outcomes? That's a causal question. Now, the problem is, if I have this retrospective data where people are living where they're living and oil wells are being put where they're put, in that data, what is the time? So the exposure would be, let's say I just binarize it to somebody living within a mile or not living within a mile. When is it that they began? When is it that they were living there? It's not really clear that, is it when they moved there? What if they were born there? So it's not totally understood. What do you mean by that intervention? So you have to imagine some kind of intervention where somebody might be moved away or something like that. So when is it that that's happening? The treatment is actually not really that well defined in that case. So it's actually kind of difficult to do this. And you have to be a little bit creative and think about how you're going to formalize your question in a way that you can at least start to think about these problems. Of course, you can just say, hey, whatever. We're just going to look at it anyways and pretend all of this stuff holds. But and that's a limitation. Sure, there's always going to be limitations, but I think it does help to at least try to wrap your head around it. A similar problem is, when did no exposure happen? So let's say you want to know, are people who take this drug, metformin, going to do better in terms of controlling their diabetes than people who are not taking the drug? And the problem is, if you have retrospective data, you have people who took the drug, you have people who didn't take the drug. So for people who took the drug, you know what happened after they took the drug. You know when they started taking it, and you can see what happened after. But for the people who didn't take the drug, when is it that they started not taking it? They were never taking it. So there's not really a clear, time that you can say, oh, I should adjust for everything that's after this time, or I should not adjust for anything that's after this time, but I should for anything that's before that time. It's not totally obvious what to do there, and there's, again, not a lot of courses or stuff where people actually give you concrete advice on how to deal with this. But the clearest thing to do is to define an index time. So, for example, the time at which the first doctor's visit after their diagnosis, and see, did they get metformin there or did they not? And so then you've clarified your question. It's not what is the effect of metformin versus not metformin. It's what's the effect of metformin being prescribed on your first doctor's visit. Because then it's clear, if somebody has a doctor's visit after diagnosis and they don't get metformin there, that is the time at which they do not get metformin, okay? And it doesn't matter if they get metformin in their second or third or fourth doctor's visit. Doesn't matter, because that's not part of the question that you're asking. You're just asking, what's the effect of not getting metformin at the first doctor's visit? And of course, that kind of narrows the scope of your question, but it makes it much, much easier to make sure that you're answering that question well. Because then you can clearly say, anything that happened before the first doctor's visit, I can adjust for. Anything after that, I should not be adjusting for, okay? And then, okay, maybe somebody says, well, that's not the right question. Really, what you need to be asking about is the second doctor's visit, or some kind of weighted combination of these. Sure, whatever, do that, right? But each of those questions, you can adjust for the right things in those specific questions, and then come up with a more, a big picture gestalt answer based on the clear answers to each of those specific questions. So my point being, generally, these problems pop up in observational studies all the time, and you can do a lot better by just thinking a little bit more clearly about your question. Also, if you're working with a biostatistician, this is the kind of thing that they should be asking you about. A lot of people don't. A lot of biostatisticians are a little too concerned with the model and not really thinking about the question. But this is really the thing they should be able to try to clarify for you. It's everywhere, right? There's so many papers about this kind of stuff. Immeasurable time bias. This is basically where you don't know when something happened or didn't happen, and therefore you can't measure the outcome in a particular period. Asking about, can cross-sectional studies actually be useful? Because cross-sectional studies, everything's measured at the same time, so you kind of don't know the order of things. And that makes it very difficult to know that you're not conditioning on confounders, or even that the exposure is affecting the outcome and not the other way around. So all of this is really thinking about your data, thinking about your question very clearly. So these are the fixes. Here, define your intervention clearly. Here, define your index time clearly. Even if it's not really the way that it's done in the data, at least you can think abstractly and think about how might I improve this experiment for the next time around. Put that in your discussion section or report to your whoever your supervisor is in that kind of way. And that will actually help you move forward instead of doing the same dumb thing over and over and over again. So a really useful overall framework, these two things that kind of fall into is this target trial emulation idea. And really, we've been talking about this, like all of this causal inference stuff is, falls under this. But the reason why I like this is because it's very concrete and it helps people do all that stuff implicitly without even understanding all of the math or whatever. So what is target trial emulation? The idea is if you're doing a retrospective study or any kind of non-randomized study, before you even do anything, before you look at that data, analyze it, any of that, think about first, what is the ideal thing that I could have done? If I had infinite money and I had infinite time and I didn't have, any people dropping out of my study and I, could randomize whatever I wanted, okay, first think about that because that will actually help you understand what's the question that you are trying to ask. And in that case, you don't have to think about any models. You don't have to think about anything because you can imagine, what if I could directly observe, two parallel universes where in one universe I did this and in another universe I did that. So forget about regression models, forget about statistics because there's no sampling variability because you have infinite data, okay? So it's purely thinking about everything in this kind of population framework where you can randomize and making it that concrete. Oftentimes people can't even articulate what they were looking for, in my experience, because people will say, "Oh, I would just do a linear regression and report the coefficient." I'm like, "No, you're not thinking, right? Like, what does that mean? What if you had infinite patients, you wouldn't need the linear regression. There'd be no confidence interval to think about, right? So you really got to pin people down like that in practice. But it's super helpful because it's a very concrete way to do it. What is the randomized trial that you would have run if you could have? Then you go back and you look at your observational data and you say, okay, what's kind of messed up, right? Well, okay, it's not randomized. So, so I have to kind of adjust for confounders, but also the more practical things. In my randomized trial, when would I have given the treatment versus not treatment? So, for example, this issue of index time is addressed by this because in a randomized trial, if I'm randomizing metformin and not metformin, I have to specify what time I'm enrolling people and when I'm going to give them the placebo. So I can't just say people who, I don't have like a one-arm randomized trial where I just give people a drug at a particular time. I also have a control group, and I need to decide when is it that I'm giving them the placebo. Is it at the first visit? Is it at the third visit? Right? So it makes that obvious. Anything that you're doing in a trial, you have to try to be doing in the observational study as well in some way, or somehow replicate that process to try to get good causal inference. So I recommend you check this stuff out, read this paper, read all the papers that have been published after that. It's a nice concrete framework. It's not revolutionary. It's just a different way of talking about it so that people who are more applied and are used to thinking about randomized trials can actually do this kind of stuff and ask the right questions. So here's another paper written recently, comparison of target trial emulation framework. I like this one because it really gets at the issues here. So in the traditional approach to clinical research, analysis proceeds first postulating a regression model according to the type of data. So if you have a time to event outcome, you use a Cox regression model. If you have continuous outcomes, people use linear regression. Okay, the coefficients of the regression model are used to answer the clinical question. This is the model first, but this is bad. Okay, regression coefficients, as we've seen, do not represent quantities of scientific interest generally. And then secondly, you have a lot of assumptions that go into the specific regression model that you're using, and they're rarely correct. Thirdly, there's this kind of time-dependent feedback. We haven't really looked too much about that, but the regression models by themselves obviously don't know about the order of things, right? You have to know what order of things. This is a little bit of what we're talking about. What's a confounder? What's treatment? What's an outcome? What is a collider potentially? One more thing. So fourth, we have this tendency to interpret all the coefficients, but we know that most of those are meaningless. We don't care about the coefficients at all. We just want to extract an ETE, right? And then finally, the model selection stuff, which we just talked about earlier, in this lecture if we're not accounting for the variance induced by that. So I just love this because it's just nailing all of the things that we've talked about. However, you don't have to do that. You can do better stuff. So you can do target trial emulation. You can think more clearly about when the index time is. We can follow this roadmap for causal inference. We'll talk a little bit about that in a couple weeks. And you can ask the question, and then think about what would you do ideally, and then how do you kind of account for the shortcomings in the data relative to what you're doing ideally. So that's what's basically discussed here. All right, so let's try to practice that. Let's say you're reading an observational study. The authors compare survival times of cancer patients. So survival time is just a continuous measurement, right? Between groups on two different kinds of chemotherapy. Would it be advisable to adjust for each patient's age at the time of death, their age at the time of chemotherapy, their birth year, or any of these that have a significant p-value in a univariate regression model for the outcome? So think about this for a minute. Okay, so the exposure here is what kind of chemotherapy they're getting, okay? And what we've been talking about is we don't want to ever really adjust for things that happen after the exposure. And for them to get this kind of thing, they have to still be alive, obviously. You don't want to give dead people chemotherapy. Therefore, their age at the time of death, this is something that happened after the chemotherapy. This was measured after the chemotherapy. So we don't want to do this. Each patient's age at the time of chemotherapy, fine. Their birth year, that happened before chemotherapy, fine. Any of these that have a significant p-value in a univariate regression model for the outcome, no. No, absolutely not. Because you cannot test for what is a confounder and what is a collider. So generally, things that happen after the outcome, a lot of them will be affected by the outcome. And so you're going to have a pretty significant association. But you can have very significant associations between those things. So, patient's age at time of death, that's going to be very significantly associated. There's going to be very old people with probably with how long they lived after chemotherapy. There's no reason why that shouldn't be associated. So you would actually be kind of selecting some of these variables that you don't want to include. But this is an interesting example because a lot of times people just say age, right? Should you adjust for age? Okay, but maybe. What age? What age are you talking about? Their age when? So these two, you might think, okay, if I know their birth year, I know their age at the time of death. Well, only if you know what time they died. And if you know what time they died, then that was something that happened after the chemotherapy. So you shouldn't be adjusting it. So you really got to be thinking about things like this. Similarly, cross-sectional studies will say, we measured income, we measured SES, blah, 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 all this stuff. When did you measure it? Is it this year? Which is after the exposure. We asked people, when were they exposed? Oh, it was 5 years ago. And then we measured their SES this year and we adjusted for that. Okay, maybe you should have asked when the SES was measured 10 years ago, right? Or what was your income 10 years ago or something like that. That would be more sensible.